In this short video, we will rewrite classical electron theory with Coulomb fields that radiate at the speed of light. We do this most simply by redefining the Coulomb fields as momentum flux fields. While this is a rather flagrant violation of conservation of energy, we will show how radiating Coulomb fields provide for a much more reasonable theory of the classical particle. Specifically, radiating Coulomb fields require the classical electron to possess a classical radius. They eliminate the divergent self-energy and stabilize the classical electron at the particle radius. And finally, they provide an algorithm for quantizing the particle. A more useful approach to the problem of the classical electron begins by writing the covariant vacuum gauge condition given by this formula. This is a first-order differential equation for the potentials, which is solved by the vacuum gauge null potentials shown here. We are interested in developing a Lagrangian formulation for the classical electron with vacuum gauge potentials. For this, we can remove from the potentials a constant 4 pi times the fundamental surface charge density, and this introduces a particle radius while defining a vacuum displacement vector. In analogy with the theory of elastic media, now define two second-rank tensors. Let eta mu nu represent a vacuum strain tensor, and let delta mu nu represent the associated vacuum stress tensor. We see that the vacuum stress tensor is multiplied by a force constant mu sub e equal to 4 pi times the square of the fundamental surface charge density. In addition, this force constant is exactly the outward pressure of the classical electron charge density, tending to explode the particle. Finally, the presence of the metric tensor indicates that our vacuum stress tensor is endowed with a time-like restoring property and a space-like admissibility property. Now suppose we calculate the forward divergence of the vacuum displacement vector. This determines a scalar quantity which we will refer to as a vacuum dilatation. This is a measure of the amount by which our classical electron is compressing the vacuum in its near neighborhood. With this definition and definitions of vacuum stress and vacuum strain, we are now in a position to draw from the three-space theory of elastic media and write a vacuum Lagrangian for the electron. For consistency, this will require a redefinition of the traditional point charge density in the interaction term, which is now replaced with a new point force density, F nu sub e. Unfortunately, this Lagrangian cannot be considered as complete because it must include an additional term to propagate the velocity fields. For this, we observe that the vacuum Lagrangian possesses an internal symmetry under a variation of the vacuum stress tensor proportional to the metric. Inserting this into the vacuum Lagrangian generates an additional term proportional to the vacuum dilatation as indicated by the red arrow. Of course, this linear term does not change the equations of motion, but as we will show, introduces linear stresses associated with the motion of the vacuum field propagating from the source. We are now in a position to use Lagrangian mechanics to calculate the canonical stress tensor for the vacuum gauge electron. There are three quadratic terms indicated inside the bracket, and the red arrow points to a single linear term. The quadratic terms must be symmetrized, similar to the conventional electromagnetic theory, which is accomplished by removing a term having a zero divergence. In contrast, the linear term does not require symmetrization and is proportional to the transpose of the vacuum stress tensor. Remembering that we are not considering particle accelerations yet, the resulting velocity stress tensor for the vacuum theory is shown here. You may be surprised to find out that the terms enclosed by the horizontal red bracket are exactly the symmetric stress tensor for the classical electron. But of course, the vacuum term is new. To include particle accelerations, we extend our definition of vacuum strain to include an acceleration strain component. The acceleration strain is the bilinear quantity shown here and composed of the vacuum displacement 4 vector and the perpendicular acceleration 4 vector. Like the velocity strain, the acceleration strain is a unitless quantity and is generally a very small correction to the velocity strain. This qualifies the acceleration strain as a perturbation to the velocity theory. We are now in a position to calculate the most general form of the stress tensor for the classical electron. To do this, we insert the new strain tensor in the quadratic portion of the stress tensor, which inherits 3 extra terms. Once again, you may be surprised to find out that this generalized stress tensor is still exactly the stress tensor for the classical electron under the most general motions of the particle. As a final step, let's define the quantity r mu nu as a bilinear combination of strain tensors. This allows the total stress tensor along with the radiation term to be written as shown here. Of course, this set of equations has a very Einsteinian appeal, which can be used to show particle stability. For this, we define 2 second-rank tensors, g mu nu 1 and g mu nu 2. With these definitions, the velocity portion of the symmetric stress tensor and the vacuum tensor can be written as shown here. Next, we can cast the velocity stress tensor, including the vacuum correction, in terms of our tensors g mu nu 1 and g mu nu 2. By doing this, we find that the quadratic stress is removed at the electron radius defined by eta equal 1, or equivalently when rho is equal to r sub e. What's left at the particle radius is then a tensor E mu nu sub rad, which is proportional to the covariant derivative of the null vector r mu. We can show the vacuum gauge particle in a space-time diagram. Here we see the track of an electron moving at velocity beta nu, and the instantaneous radius of the particle as the red circles. For all times, this radius lives on the light cone and is causally connected to the retarded time where the signal was emitted. We note here that the present time location of the electron is not at the center of the sphere, except in the particle's rest frame. Now let's calculate the energy density inside the particle radius. We do this by contracting capital E mu nu with the metric tensor. This gives us scalar E rad equal to the mass energy of the electron divided by the volume V sub E. This volume is that of a 3-sphere enclosed by the red rings in the space-time diagram. This sphere, not surprisingly, has a radius equal to the classical electron radius. Finally, let's quantize the vacuum gauge electron by calculating the Dirac energy momentum tensor. We do this by first writing out the stress E mu nu sub rad term by term at the particle radius. Now let's write this formula again with some redundant terms multiplying the metric tensor. So far, we've done nothing to E mu nu sub rad, but now let's quantize the tensor by making some well-chosen substitutions. The first 2 substitutions are well known to the field of physics, but the last one is new. Here we are replacing the covariant space-like vector with a set of Dirac gamma matrices. When we do this, it's easy to show that the quantized tensor becomes a new tensor we are calling E mu nu sub Dirac. Now let's apply Dirac spinors to both sides of E mu nu sub Dirac. When we do this, we find that the resulting tensor is 0. Moreover, the sum of all the terms that make this tensor 0 is an equation for the transpose of the Dirac energy momentum tensor, and we can write this tensor according to the formula shown here. Now let's summarize this derivation with the statement that we are permitted to rationalize a classical radiating particle, and we are also permitted to rationalize a quantum mechanical particle, but not both at the same time. They are, in fact, mutually exclusive versions of the same thing. For a final calculation, it is useful to calculate the free particle Dirac Lagrangian by contracting indices on E mu nu sub Dirac and sandwiching the result between Dirac wave functions. Of course, we need only apply Lagrange's equations to reproduce, once again, the Dirac energy momentum tensor. In summary, the vacuum gauge condition allows for a theory of the classical electron having similarities to the 3-space theory of elastic media. The notion of an invariant particle radius is instrumental in making the classical theory work, and evaluation of stresses at the particle radius leads directly to the Dirac energy momentum tensor. Thanks again for listening in. We hope you've enjoyed this short video and have a great day.